Welcome back. In this video, we'll consider the concept of harmonic functions. We have looked at what analytic functions are. I've also looked at what an entire function is. So what exactly do we mean when we say an harmonic function? Let us define it. In simple terms, cutting through a lot of red tape, we would say that W equals f of z is a harmonic function if it satisfies what we call the Laplacian equation. So what exactly is this Laplacian equation? Let us look at it. That means we are saying in these terms that if we have a function of complex variable, which of course can also be written as a function of two real variables, like so, then f of z is harmonic if the Laplacian of u equals 0 or the Laplacian of v equals 0, where of course this Laplacian is defined as the second partial derivative with respect to x plus the second partial derivative of u with respect to y. And you can also define the Laplacian with respect to v as the second partial derivative of v with respect to x, as well as the second partial derivative of v with respect to y. So the function is harmonic if one of these two Laplacians gives you 0. Now, usually both of them would give you 0, but then you do not need to check both of them. You just need to check one of them. So long as one of them gives you 0, you should be rest assured that the second one will definitely give you 0. Now, let's give ourselves an example. First, it's important to note this, that a function cannot be harmonic if the function is not first and foremost an analytic function. The function has to be an analytic function first, which would have guaranteed that the first four partial derivatives are continuous, and then it satisfies the Cauchy-Riemann equation. It is that analytic function that you can now check if it can become a harmonic function, which means you cannot have a harmonic function that is not analytic, right? So all harmonic functions are, of course, analytic functions, right? Not all analytic functions will become harmonic functions, yes, but then all harmonic functions are indeed analytic functions. So this is very, very important for us to consider. Now, let us see yet again how we can look at an example towards this. We can examine if we take e raised to power z as a sample, we have examined that e raised to power z is indeed an analytic function. It is also indeed an entire function. Now we want to see if it's an harmonic function. Now remember, we split f of z as e raised to power z, which we rewrote as e raised to power x plus iy, which of course we split into e raised to power x, e raised to power iy. And then at the end of the day, we would have that f of z, which of course is the same as f of x comma y. We wrote it as e raised to the power of x cos y plus I sin y. Now we had our u to be equal to e raised to the power of x cos y, and then we had our v to be equal to e raised to the power of x sin y. We had these two concepts locked down. Now let us carry out our differentials. We already know that e raised to the power z is analytic. We did that in a previous video. If you have not watched that video, please take a pause and watch that video so you can get knowledge of that as well. Now, in this case, we would simply take the differentials up to the second order. First partial derivative with respect to x, of course, will give us e raised to power x cos y. Then the second partial derivative still with respect to x, which is what this is. So I'll write that as second partial derivative of u with respect to x. So it means the same thing. Would have this, of course, still making cos y as our constant coefficient. This would be e raised to power x cos y. Now, on the flip side, we can have u raised to the power of u, partial derivative of u with respect to y. This time around, making e raised to power x the constant coefficient. So we would have this to be minus e raised to the power of x sine y. And then we'll have the second partial derivative of u with respect to y. This time around, e raised to the power x still remains the constant coefficient. Sine y differentiates to cos y, so we'll have this as minus e raised to the power x cos y. So what do we notice? The Laplacian of u, in this case, which would be uxx plus v plus u yy, both parts are the same, the variable is what changes. So in this case, you're going to have e raised to the power of x cos y, which is uxx, plus minus e raised to the power x cos y, which is uyy. So adding this together, you would see already that this is e raised to the power x cos y minus e raised to the power x cos y. So it cancels out, so the Laplacian gives you 0. So since the Laplacian gives us 0, thus, or therefore, you have that e raised to the power of z is indeed a harmonic function. So this is very, very important to keep in mind. Of course, we went through the route using the real part of the function, which is u. You could also decide to use the imaginary part of the function, which is v, and see if vxx plus vyy also still gives you 0. Try that out and let's know your answers in the comments. So see if you also get the same thing. This essentially shows you how to apply the concept of harmonic functions. Now that we have dealt with this, this would wrap up our discussions into the complex function as a sub part of the complex analysis module that we have written. Hereinafter, we will now extend into yet another sub portion of the complex analysis module, which is the Green's theorem portion. Now, we would try as much as possible to treat this in detail. I would also break down this complex analysis module into shorter playlists. So we have a complex number playlist, a complex function playlist, which ends with this, and then we'd also have a Green's theorem playlist, which would begin with that next video. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos.